Kia ora, it's Mrs. Goodson here, and this video is about alkenes. So it's part of organic chemistry, and in this video I'm going to explain how to name alkenes. I'm going to explain about geometric isomers, that's cis and trans isomers, and I'm going to talk about the physical properties of alkenes. Alkenes are hydrocarbons, so they only contain carbon and hydrogen, and they contain a carbon-carbon double bond. They have the general formula CnH2n. So they've got a different general formula from alkanes. They are known as unsaturated compounds, which means they have less hydrogens. So the main thing to look for alkenes is this carbon-carbon double bond. We use the IUPAC naming system, and we look again for the longest continuous carbon chain. So in this molecule here, for example, it's 1, 2, 3. So it's propene, and then it's got a methyl group attached to it. So it's methylpropene. This molecule here is a little bit longer. It has 1, 2, 3, 4 carbons. So it's bute, and then it has this methyl group. So if we named it like that, it would double bond is in the 3 position or the 2 position, so it's in the middle there, so it's butene. But we have to be careful because we could also number it from this end, 1, 2, 3, 4, in which case it would be not 3 methyl but 2 methyl. Because that gives us a smaller number, the correct way of naming it is we're going to write that out, it's from this end, so that the carbon attached to the methyl group is the 2 carbon, so it's 2-methyl-butene. And just note that the double bond has a higher numbering priority than the alkyl group and any halides. Okay, these ones don't have halides on it, but if it's got halides, they're named as groups, and so the name part would be at the front. Okay, so this is the homologous series for alkenes. The smallest alkene is ethene, and that's because you need 2 carbons to make a double bond, a carbon-carbon double bond. So C2H4, and then 3 carbons is propene, 4 carbons butene, pentene, hex is our 6 carbons, heptene is 7 carbons, and octene is 8 carbons. So straight chain alkenes use the same prefix as alkanes, but with the suffix "-ene". If there are 3 carbon atoms, more than 3 carbon atoms in the chain, then the position of the double bond must be specified with a number to identify the first carbon in the double bond. So ethene and propene, there's only one version that they can be. But from butene onwards, you have to say where the double bond goes. So you've got butene, but1ene, pent1ene, pent2ene, 1 hexene, 2 hexene, or 3 hexene. Alkenes can have structural isomers. These are molecules with different structures but sharing the same molecular formula. They arise by having the carbon-carbon double bond in a different position. So they would be positional isomers. Let's have a look at some examples. So this is an example of but1. This is but1ene. So we've got the double bond is of the first carbon. This, if we move the double bond to but2ene, then it's still got the same molecular formula, C4H8. Now remember to check that each carbon has 4 bonds attached to it, no more or no less. So this carbon has 1, 2, 3, 4. This carbon has 1, 2, 3, 4, and so on. So just check that each carbon has just got 4 bonds attached to it. Now this is another isomer, but the longest continuous chain is propene. So 1, 2, 3. So propene only has one place the double bond can go, and then the methyl group here is attached to the second carbon. So it's 2-methylpropene, and that would be an example of a branched alkene that is an isomer of C4H8. Now, here's an example of some branch chain alkenes. The parent chain is the chain which contains the double bond. So it's this one here. This has got 4 carbons. Even if we went around the corner, it would still be 4. So it's bute is the parent name. The double bond is off the second carbon there. So it's 2-ene. And then it's got 2-methyl. Okay. The position of the double bond must be the lowest number, counting from the end that gives the lowest number. Okay, geometric isomers. For this type of isomer to occur, there must be a carbon-carbon double bond, and each carbon in the double bond must have 2 different groups attached. So each carbon is to have 2 different groups. Geometric isomers occur because the free rotation around the double bond cannot occur. So this is in a single bond, so this bond can rotate. It can rotate around here. So these atoms can be in this position, this trans opposite position, or they could be on the same side, but they can move. So sometimes they're in a trans position and sometimes they're in a cis position on the same side. However, if it's a double bond, they're basically fixed. So this on opposite sides is called trans, and this on the same side is cis. So all the molecules, if they're cis, are on this side. So they are fixed in space. The double bond cannot rotate. So cis or trans isomers, they have the same order of connectivity. So the bonds are connected the same, but they have a different arrangement in space. As I was saying, if these ones here have got methyl groups on it, if they're on the same side, then it is the cis 2-butene. And if it is on opposite sides, then it is a trans 2-butene. Butene is the simplest alkene to have geometric isomers. Geometric isomers have different physical properties. For example, the boiling point of cis-butene is 3.7 degrees centigrade, and that of trans-butene is 0.88 degrees centigrade. So they've got different boiling points because the molecules interact differently. However, they usually have the same chemical properties, undergo the same chemical reactions. Here's another example. So this one is 1,2-dichloroethene. But in this example, the chlorines are on opposite sides of the double bond, so that is trans. And if they're on the same side, then it's the cis isomer. So you've got the cis isomer and the trans isomer. And just to say that this way of drawing the double bond, this way here, it makes it a good idea so that you can see. If you draw the molecule in that shape, it makes it easier to see the trans and cis isomers. So if alkenes have the same groups or atoms attached to one of the 2 carbon atoms on the double bond, they do not exhibit geometric isomers. So we had go back to what we needed for cis-trans isomers. We needed a carbon-carbon double bond, which this molecule has. But this carbon has got 2 groups that are the same, and this group also has 2 groups that are the same. So this example, which is but-1-ene, actually it's not, it's 1, 2, 3. This example here is methylpropene, but it has no geometric isomerism because both carbon atoms have identical atoms or groups attached. And this tip is just saying if you draw it in this shape, then it's easier to see the cis-trans isomerism or not. Okay, now the physical properties of alkenes. They're nonpolar molecules, just like alkanes. So they are insoluble in water and other polar solvents. Okay, so they're nonpolar. They make good solvents for other nonpolar substances. Just like alkanes, they show an increase in melting and boiling points as the molar mass or the chain length increases. So when you increase the chain length, you increase the intermolecular forces. They have densities of less than 1 gram per centimetre cubed, so they float on water. They have low density. At room temperature, ethene, propene, and butene are gases, and alkenes of high molecular mass are liquids. Okay, so that's the end of this video about alkenes, and in the next video I'm going to talk about chemical properties and reactions of alkenes. See you next time.